Swayam Prabha. Digital India. Educated India.
Very good morning, everyone. Today, I, Ronit Dyala,
And I, Devansh Banik.
of class 11, would be giving a presentation on Newton's third law of motion and how it is a part of everyday science. We would be doing it in the form of a short skit. We hope you enjoy. Hey Devansh, what happened? Physics ended 5 minutes back and you're still here?
What can I say, Ronit? These laws of motion are just so demoralizing.
Demoralizing? Wow. That's a big word to describe a feeling you get after studying something so simple like Newton's laws.
Sure, the first two laws are child's play, but the third one, oh my god, the sheer number of numericals, the derivations, and it's just purely theoretical.
Well, friend, theory and a negative attitude will only take you this far.
Alright then, Oppenheimer, why don't you show me your Manhattan project?
Sure, Heisenberg. Okay, so first of all, let's look at the exact definition of the law. The law states that for each and every action, there is an equal and opposite reaction.
Oh my god, fantabulous, amazing. That one sentence has made me understand everything. Thank you.
Hold your horses, buddy. The ship hasn't sailed yet. Once you get to know what the law states, then you would be able to identify its use and real-life applications and obviously understand the concept.
Wait, what do you mean?
Be patient with me. Trust me. All right. So now what I want you to do is sit down and do whatever you were doing before I entered the room.
Alright.
I guess you're ready, Professor. Your findings, please.
Well, I'm sitting in a classroom, bouncing around a ball, stretching a rubber band, and talking to a not so helpful person like you. I mean, come on. You told me one sentence. How is that supposed to make me understand everything?
Okay. Now let this not so helpful person help you out. Right. Remember the definition of the law and now the actions that you just mentioned. Put two and two together and you will get the result.
Wait, I get it. My action is bouncing the ball and stretching the rubber band. When I bounce the ball, I apply force on the ball, and the table puts another force on the ball, which is equal and opposite. It makes it reach my hand. Now, for the rubber band, I'm stretching it, and there's an internal force acting on it, which is also called stress. It brings it back to its current position.
Let me correct you there. Stress is not the internal restoring force. It is the internal restoring force acting per unit area of the object. Now let me explain the physics behind it. Basically, elasticity is the property of a material by virtue of which it is able to regain its original configuration after a deforming force is released. In your case, you stretch the rubber band, right? That is the deforming case in this scenario. Once you release the rubber band, it came back to its original configuration. That, my friend, is elasticity and how Newton's third law of application applies there.
This all makes sense now. Every action has an equal and opposite reaction. Eureka!
Okay, Archimedes, I'll stop you there because you forgot one.
Wait, what's that?
Sitting.
What? How?
Okay, so Mr. The first two laws are child's play for me. Can you define force for everyone present?
A push or a pull.
Okay, and
Mass into acceleration.
since you were sitting, which acceleration was acting on you?
Acceleration due to gravity. Oh, wait!
Yes, I'm waiting.
No, wait!
Oh, all right. I think you got it. So basically, when you were sitting, you applied a force on the chair, which was basically your body weight. In response to that, the chair exerts an equal and opposite reaction on you, keeping you in equilibrium and giving you the ability to sit.
That makes sense now. My mind is blown. How do you do this?
It's very easy. I mean, just how you did. Just observe and then execute.
That makes sense.
You know, Devansh, I think we've gotten an understanding of what Newton's third law of motion is. But perhaps we can revise amongst ourselves by explaining to our new friends what the law is.
Yeah, alright. Before that, Ronit, could you write the third law of motion for me?
Sure. Here you go.
Thanks. Now, when I think about it, there's the third law of motion acting on this as well. If you think about it.
Oh, yeah, you're right. I exert a force on the pen, right? Which enables it to, move on the paper, right? And then the paper, in response to the force being applied by the pen on it, exerts an equal and opposite reaction on the pen, thus enabling me to write.
How the tables have turned. I think you forgot something there.
What did I forget?
There is a resistive force acting when you're applying force on the pen. Now, when you're writing, there's a resistive force acting which makes a mark on the pen. That, my friend, is friction.
Oh, now that I look at it, you're right. I think it's similar to walking if I'm not wrong, right? So basically when I'm walking, I exert a force in the backward direction, right? And then in response to that, the ground exerts an equal and an opposite reaction on my foot, making me move forward. And friction, as you mentioned, opposes the relative motion that I'm performing, and because of that, I do not slide or fall, and I simply move on.
Well, Professor, it seems that we've seen so many direct examples of the third law. Are there any more metaphorical examples?
Sure, there certainly are more metaphorical examples. However, just your disclaimer, obviously these metaphorical examples are not directly related to Newton's third law of motion and are just another way of helping any common man understand what Newton's third law of motion is without the science behind it. Okay, now Devansh, can I have that pen that you just made me write Newton's third law of motion with?
Sure.
All right. Okay. Let's suppose I want to sell this pen to you for 20 rupees. Would you buy it?
Sure, why not?
However, if let's say I increase the price of the same pen I was selling to you to 5 crores.
5 crores? Are you out of your mind?
Exactly. Once I increase the price, the customer who was willing to buy it at the original price does not want to buy it considering the price increased. And this is precisely the law of demand as well that we see in economics, right? If we consider the action of increasing the price to be the action, right? And then we see that the demand for the product goes down, that is the reaction towards it, right? Obviously, there is more economics behind it, and it is not directly related to the Newton's third law of motion. But I think it's a good example to explain.
Yeah, definitely, I agree. That's a nice example.
Okay, Devansh, for the next one, I want you to be truthful, not just to me, but to everyone present.
More of your riddles then. All right, I'll be truthful.
Okay, have you ever used any chatbot like ChatGPT to do your work? Okay, I'll take that as a yes. Obviously you have. Okay, so let's take the example of ChatGPT as a chatbot. Once you input a command into it, let's say you want to complete your assignment, right? You write the question that you want the chatbot to solve, and in return, you get an exact answer of what it is, right? Yeah. There's no ifs or buts, just the direct answer that you were looking for. So if we take the question to be in the action, you get the answer as an equal and opposite reaction.
Yeah, that's another good example. That's really good.
You know, Devansh, I find it so interesting that to explain this law, we do not require any full-fledged experiments. All we need to do is to learn and observe what is happening around us. Real-life applications.
That's true. You know, when I come to think of it, I think there are some important points we should also be mentioning.
Yes, you're absolutely right. Now, for example, all of the situations that we've observed so far, we see that there is a necessity to it. There must be two or more objects acting in that particular situation. Because if that bare minimum is not achieved, then the law will not hold true as there is no action or no reaction.
Yeah, that's right. And not to mention, there are many different forces. Like there's friction, there's air drag, there's air resistance. All of these are also what accumulate to be the reaction force.
Yes. So for example, when I was walking, frictional force was not the equal and opposite reaction because friction was actually acting on two objects at the same time. It was opposing relative motion. Hence, it was a part of whatever I was doing in that situation, walking and even in writing.
Yes. See, we don't notice these things at first, but when we look into the concept, we learn the concept and we understand it. It has become so easy to apply what we have understood instead of resorting to all this horrifying rote learning.
Yes, you're absolutely right. And you know, I think in the end, after all of this, we have finally not only understood ourselves, but have explained to everyone that for each and every action,
There's an equal and opposite reaction.
Thank you.
Thank you.